So we start this last session of this workshop with Lorenzo. He's going to talk about a quantum solution to the error of time dilemma.
Okay. Let me start by thanking the organizers for accepting my paper. I thought this conference would contain more foundations. That's why I submitted this paper. But it has been a very nice conference, and I really enjoyed being here. Since people have been asking, the pictures have nothing to do with the talk. They're just to keep people awake. Okay, so I'm going to talk about a quantum solution to the arrow of time dilemma. It's kind of a crazy idea, but as you will see, it emerges quite naturally in the framework of many worlds, quantum mechanics. And of course, if you look at the ideas that are out there, they're quite crazy too. So I think that, for example, this is Scientific American of this month. I just picked it up in Copenhagen airport. Why does time only move forward? Page 26. So you can look it up there. It's even more crazy than what I'm talking about, because he says something about universes that exist prior to the Big Bang. I didn't even think that there could be something prior to the Big Bang, and universes in which time goes backwards. All sorts of weird stuff here. Okay, what am I going to talk about? Essentially, I'm starting from the Low-Schmidt paradox, which is an objection that was given to Boltzmann when he proposed his statistical interpretation of thermodynamics. And essentially is, how can we obtain an irreversible phenomena from reversible time-symmetrical physical laws? So this is, and essentially entropy is constant if you look at reversible transformation, and the microscopic dynamics is governed by reversible laws, for example, Schrödinger equation. So how come does entropy increase? Okay. This is, of course, a problem for the statistical interpretation of the second law of thermodynamics. And there are many proposed solutions, such as the one I just showed you, which is probably the most recent. But each of these has problems, and the matter is not settled yet. I think everybody agrees with that. Some solutions are the graining of phase space and trace, and interaction with heat path, or even changing the microdynamics so that it becomes irreversible. Okay. So what's the hypothesis that is behind my idea? I suppose that quantum mechanics is valid at all scales. As I was saying, this is true in, for example, in the many worlds framework. And I think that is plausible because of Occam's razor. We don't have any reason to think that things are not like that, because there are no experiments which violate quantum mechanics up to now. But of course, this is a highly controversial hypothesis, and the standard approaches typically don't take this as valid. For example, in Copenhagen interpretation, you have measurements which are not described by quantum mechanics, and similar approaches. Of course, this will be settled by experiments when a superposition of a measurement apparatus is demonstrated, or if it's proved to be impossible. But for now, let's use this as a working hypothesis. I think this is reasonable. Okay, and so now I'm going to talk about entropy and its relation to the second law. What is thermodynamical entropy? There are many different ways to introduce this quantity, but essentially it is a quantity that measures how usable energy gets degraded into heat. So how energy goes away and it cannot be used anymore. In quantum mechanics, we are used to dealing with von Neumann entropy, which is basically a quantity that measures the amount of information that is contained in a system, and it's given by this expression here, as you all know, minus trace rho log rho, where rho is the density matrix of the system. So these two quantities, when applicable, these two quantities coincide. That is, for systems which are in thermodynamical equilibrium, And the fact that they coincide was shown by Einstein, and then Paris gave more refined proof, but we don't really need this. All we need is basically the fact that we can convert bits of thermodynamical entropy into bits of information and vice versa. And we know we can do that by using these thought experiments, which are Maxwell demons and Szilard engines. They can do this conversion. And this is all we need, actually, for what I'm going to talk about. So, now let's go to define information. Of course, information is physical. This is Landauer's mantra. I mean, this is something you hear at the time. This means that anything must be recorded into a physical degree of freedom. Information by itself does not really exist. Information exists only if it is encoded somewhere. And of course, if we take a record of an event and we decorrelate it from that event, that amounts to erasing that event. Okay? So, for example, if we have a description of some experiment from a piece of paper or in a hard drive, and then we erase that description, that means that we are decorrelating the information from the event. And of course, we can erase the event in the sense that if all the records of the event are radically erased, then the situation is indistinguishable from the event not having happened at all. What does that mean? Clearly, it's not sufficient to erase it like with a rubber eraser or delete something from a hard drive, as I was saying before, but we must ensure that in principle it is impossible to recover the information that we have erased in any possible ways. Okay? So in that case, if we erase completely all the correlations between the event and the physical media in which the event was encoded, then this situation is indistinguishable from the situation in which the event did not happen at all. One example is that we can invert the dynamics that correlated the event and the information carried in the first place. For example, this is a way to radically erase the event. Now, what happens if all the records of the events are erased? Suppose that the event was something that increased the entropy, then its erasure will decrease the entropy. And of course, there's no second law violation, because this situation is indistinguishable from the event not having happened. Okay, so that sounds pretty weird, but can this really happen? And of course, under the hypothesis that quantum mechanics is valid at all scales, we can say that this can happen, and I'm going to show a couple of thought experiments that show this point, and then I will give a more general, detailed theory of this. But let's start with the first, a very simple experiment. Now, we have Alice inside her lab, which is completely isolated, and she's performing a Stern-Gerlach experiment, very simple. Initially, the spin is in the state left, which is a superposition of up and down with equal weights. So we have a pure state of the spin, entropy is equal to 0. Now she measures in the up-down basis, and from her point of view, the state has evolved into a mixture of up and down with probability 1/2. So entropy was created by the measurement. Alice's measurement has created 1 bit of entropy. This is all pretty standard. But now suppose that Bob is outside her isolated lab, and from his point of view, since this is completely isolated, it has a unitary evolution. So from the point of view of Bob, Alice's measurement is just a correlation of her lab's degrees of freedom with the spin. So she starts with a spin which is in a pure state, and from Bob's point of view, she ends up in a pure state of the spin correlated with her lab. Okay. So a pure state has evolved into a pure state, supposing that initially the lab was in a pure state. So from Bob's point of view, Alice's transformation has created no entropy. And now, since he's outside the lab, he can flip a switch and erase or invert Alice's transformation. Okay, so Alice's measurement was this transformation from Bob's point of view. Now he flips a switch and he decorrelates Alice's measurement from the spin from Alice. Okay, that's just a C-naught transformation. This was kind of a C-naught transformation, and the C-naught is its own inverse, so that's all he needs to invert this Alice's measurement. Of course, from a practical point of view, this transformation, this flipping of switch is incredibly complex and practically impossible, but in principle it is possible. And the important thing is that Alice must have no memory of what the measurement result was. Otherwise, this decorrelation cannot take place. So at the end of the story, she will not know what the measurement result is, and the final state has zero entropy, both from Alice and from Bob's point of view. So now, if we analyze this experiment from her perspective, a bit of entropy was definitely created when her measurement was finished, but later it was erased by Bob. So initially we had zero entropy, then we had 1 bit of entropy, and at the end we go back to zero entropy. Does that mean that we have a violation of the second law? Of course not, because in the end Alice cannot remember what the measurement result was. She will remember that she had measured the spin, but there is no way she can remember the result. So, okay, so this was a thought experiment that was more connected to the von Neumann entropy. Let's go to a second thought experiment, which is more related. It's a more complicated situation, but it relates directly to the thermodynamical entropy. Okay, so now we have, again, Alice inside her isolated lab, at least only the degrees of freedom can only enter and they cannot go out. And we have Bob that is sending a light beam to Alice in a pure state, in a single mode. But Alice does not know the state and does not know which mode he is using. And she uses many small uncorrelated detectors to recover the energy that Bob is sending her. And now we use a very nice result, which also Andreas collaborated to, that says that almost any subsystem which is small enough of a system in almost any pure state is basically in a canonical state. Okay, so Alice is ignoring the correlations between she's collecting the light using many small detectors which are not mode matched with Bob's, and because of this property, all she sees is basically thermal radiation at her detectors, and she feels her detectors that heat up, and her entropy has definitely increased. Her thermodynamical entropy has definitely increased, even though Bob just sees a unitary, reversible evolution of her whole lab, because it's isolated from the outside. No information can leak out. So again, he can apply another unitary transformation to recover all the energy that was sent into Alice. And it seems that even though this energy at some point was definitely thermal energy, so it seemed it would be locked away from reuse, and it certainly is from Alice's point of view. It's not so from Bob's point of view. Okay? So Bob can recover all the energy. And of course this looks like a violation of the second law from Alice's point of view, but it is not, because at the end of Bob's last unitary, Alice cannot remember having seen thermal radiation at her detectors, so there really isn't any violation in some sense. Okay, and all this comes about because just like von Neumann entropy, we can say that thermodynamical entropy is also subjective. It's something that depends on the state of knowledge of the observer. Although this, of course, in any practical situation, this is completely irrelevant because correlations in macroscopic objects are really too complex to track and to employ. So everybody just thinks that uses thermodynamic entropy as an objective quantity, and for all practical purposes it's certainly objective. But if you look at this, at these kinds of very weird situations, then you have to conclude that also thermodynamic entropy is subjective. Okay. So now these ideas I showed you in these thought experiments can be made rigorous and proved for arbitrary systems. And it's very easy to prove this relation here, where delta S is the variation in entropy between the final and the initial state. And we have the system A, which is Alice, the system C, which may be the spin or some other system. And then we have a reservoir, and then we have the quantum mutual information between Alice and the system she's considering. Okay, so what does this relation say? It says that basically any interaction that decreases the entropy of two systems either increases the entropy of a reservoir, which is quite obvious, you can always do that, or more interesting, it must decrease the quantum mutual information among these two systems. Okay, and the proof of this is very, very simple. All we have to do is basically consider a reservoir just as a purification space. You insert that into this quantity here, and you just see that it's zero. So it's really very, very simple to prove. And this also entails memory erosion in the sense that the quantum mutual information is basically telling you how much quantum information the system A has on the system C, and that's of course an upper bound from mutual information. If this quantity goes to zero, then also the mutual information must go to zero. And also if this decreases, then the maximum amount of information that Alice has about the system C must also decrease because of this expression here. Also, this is quite easy to prove. This has been known for quite some time. Okay. And of course, just before concluding, just a few remarks about quantum cosmology. And of course, if you look, a lot of cosmologists use the hypothesis that quantum mechanics is valid for the entire universe. That means that the evolution of the whole universe must be unitary. And then we can safely say that then the global state of the universe is pure and always maintains its purity. And to us, which are inside the universe, it doesn't appear so just because we are part of the universe. So globally, I mean, universally, there's a zero entropy all the time. And like Alice in her isolated lab, we may perceive an increase of entropy, even though this, from an outside observer, of course, no outside observer exists, but it would appear constant. Okay. So this, of course, gives a possible solution to the huge problem in cosmology and thermodynamics, which is, why does the initial state of the universe have so less entropy than today's state? Okay, but of course, all the reasoning I have done does not really require cosmological ideas. It can also be applied to finite systems, as we saw. Okay. So in conclusion, I gave a possible quantum explanation of why entropy increases. Entropy decreasing transformations can happen, as they should for if you have time-reversible microscopic dynamics. And they even might be quite common, but they cannot leave any memory of their having happened. So they are completely irrelevant to physics. If we look into our past, we cannot see these entropy decreasing transformations. Okay? So it's pretty wacky, but I think that you're almost forced into it if you take the many worlds approach to quantum mechanics. And this, of course, gives also quantum explanations on why the initial state of the universe has so much less entropy than the state we see today. The universe may well be in a zero entropy pure state, but it does not appear to us to be so. Okay? So the take-home message is that entropy can increase or decrease, but only increases can be remembered. This is my email address, and this is the preprint where I put these ideas. Thank you for your attention.
Any questions, comments? Jamie?
The second law of thermodynamics and increases of entropy, that's the sort of thing that really should apply to large values of entropy in large macroscopic systems. Is it really safe to talk about very small increases in entropy? I mean, the second law of thermodynamics doesn't say at all that your entropy can't go from 0 to 1 and then back to 0. It just says that on very large scales, over large amounts of time, it generally must increase. But microscopically, entropy can do anything.
Yeah, I agree. That's why I gave this you're probably referring to the first thought experiment that I considered, in which you have a single spin and the entropy could increase and then decrease. But of course, as I showed in the second thought experiment, you can easily extend those ideas also to microscopic systems, in which you have like a big beam of light with many degrees of freedom, and there isn't really anything here that says that I'm limiting myself to microscopic systems. So this applies equally well to microscopic and macroscopic.
Any other questions, comments? Yeah, okay.
So you must be taking a very different point of view from traditional statistical mechanics, because if I remember, I mean, Boltzmann had some sort of tentative ideas to deal with this paradox. I mean, basically coarse-graining, and he would say, well, the second law is a statistical law, right? Entropy can be assigned to the state of the system at any time, but it increases only typically. Yeah, I mean, he allowed for decreases to happen, but these are purely classical, and you can remember those. So I mean, I don't understand.
Yeah, but there is no way you can decrease the entropy back to 0. I mean, they can decrease, but those are fluctuations which are very rare. And they cannot really. There's no mechanism for them to happen. Like, also, this fact that...
I agree, yeah. So, I mean, I shouldn't take this slogan too literally. It's...
Okay, yeah, this is just to condense in a single catchphrase, but yeah, yeah, for example, Boltzmann was saying basically that the initial state of the universe has so much lower entropy than what we see today because of a tremendously improbable fluctuation that brought it there. This, of course, I mean, it has been criticized in many, many different ways. The first way to say is it's much more probable that the fluctuation would bring the universe like a fraction of a second ago. The state was a fraction of a second ago, together with the memories of us having lived more than a fraction of a second rather than 13 billion years ago. I mean, there are many objections to this kind of ideas by Boltzmann, but I don't know. I think that somehow, if you take the many worlds approach seriously, you're kind of forced into something like that. But I don't see any other mechanism where this will.
So I kind of totally agree with what you say, but I still don't see quite how this should apply many worlds.
Oh, no, I'm not saying that.
Okay.
many worlds is just the hypothesis from which I'm starting. I'm not saying that if you start from many worlds interpretation, then this seems quite natural mechanism to say that to join the second law of thermodynamics together with quantum mechanics. But I'm not saying that this tells us that the many worlds is a good deal. I mean, far from that.
So, but another assumption would be just the usual cosmological assumption that the universe, so you don't need many worlds there, you just assume the universe to have really evolved unitary, then basically you can make this argument too.
Yeah, I mean, yeah, there is problems of semantics with many worlds. When I'm talking about many worlds, I'm saying the universe evolves unitarily. That's all I mean by many world interpretation. Sorry, I should have specified that because there are so many worlds interpretations out there that possibly that's all I wanted to imply. Yes.
No more questions? Every time speak again.